Hiya, friends. Sorry, I'm ripping in at the last second. So let's see here. Let me share a screen real quick. Just want to make sure everybody's on board with that. I already do this the other day with what's sitting in here in my open math for you. We aren't going to use it like it's not your homework assignment, but it's just my way of being able to give you stuff. So this exam one test notes, like we're going to be using that today. So get yourself a copy of that, print it if you need to, don't if you don't. But this business right here, like I mentioned the other day, the law of sines and law of cosines reminder, but I'm going to be teaching you about this today, which is sort of three-dimensional version of what we've talked about already. So make sure you got access to that, print it if you need to, like I said. And then there's already test reviews in here and class notes every day when we leave class. I am going to post whatever I write on, and then also the lecture, because this Zoom is automatically recording. So that's always in there for you to rewatch anything that I say, or if you miss part of a day or whatever, you can always go in and kind of get that. And then this mechanics, I'll say this really quick too, because I will forget to say it. But I have, played around over the course of time with looking at different videos and so forth, video websites that I found. And these are just awesome. These are good ones, I guess is what I'm saying. This isn't just some random one I found. Structure Free, this guy is legit. I love this guy. He's like some Hawaiian guy that he makes sure that you don't know who he is or where he lives and so forth. So, you never know who he is, but his videos are outstanding. So this is just a link to an entire playlist of videos. And this is a little more boring. Jeff Hansen from Texas Tech. It's a little more boring, but he's really good too. And so, in the end, I'm not getting to enough examples in this class. And if you just want to deepen your understanding and have time, he's, in a sense, these guys are teaching the way I'm teaching, in the sense that they're giving a problem and just talking it through and so forth. But those are really good. So anyway, if you find yourself not feeling like you're getting enough input, you can always do that. So take me up on that. Make sure you're kind of in there and going. And this is where I'll be posting your tests and so forth. When it's time to take a test, I'll be posting stuff in there for you. So looks like you're all up and going now. Let's see, is that true? Are you all up and going? Ian, Ben, Daniel, Aaliyah, you're not in here yet. Who else isn't in there? 1, 2, 3, 4, 5, 6, 7. Looks like everybody else is in there but Aaliyah. So anyway, get in there, stay after class, ask me about it. Let's get you going. Also, I keep forgetting to actually do this. I said it with you guys the other day, but I have office hours from 12:30 to 1:30. Basically every day, Monday through Thursday. So what I'm going to do, and I put the link in my syllabus, it's just a Zoom link that's always going to be there. If you ever want to meet with me outside of class, that will be the link. Oops, that was already done. So jump in there and take me up on that. But then thirdly, because that time slot might not always work for you, you can always send me a text, and I will more likely see that than if you send me an email. So if you send me a text, and again, I'm not going to probably put your name in my phone because I have like 50 students, so I can't really put everybody's name in there. So make it a habit of saying, hey, this is Ian or whatever. And if you text me and it's like 3 o'clock and I'm sitting at my desk anyway, and you say, hey, can we Zoom real quick about question 2.7 in the assignment or whatever? And, I'll text you back and say, yeah, heading to our room. And then, we can pop on there and talk for sometimes just one-on-one interaction for 60 seconds is all it takes for you to go, oh, I totally get that now. And then we're done. I'm like, don't feel like you're imposing on me. I already know this stuff. For me to say it, not interesting. For you to get it, that's interesting. I'm not teaching this stuff just to hear myself talk. I want you to get it. So I expect you to bug me, but you got to have some maturity about that. I'm inviting you to do it, and I obviously wouldn't be giving you my cell phone. I doubt any of the other teachers are giving you their cell phone. I wouldn't be doing that if I didn't want you to take me up on it. And if I can't, or if I say, I'm out, I'll be home at 3, does that work? Like, we'll set up a time and then we can, Zoom and I'm sort of thinking 24/7, 365 here. Like, Sundays are okay. I'll just tell you I can't if I'm doing something or whatever. But again, what you should be doing is, I saw Evold emailed me scans of his first homework assignment. I haven't looked at it yet. But I'm not writing a due date, but I want your homework for this chapter 2 stuff before we start the next stuff next week. So be thinking about that. So this is really from the 2.4 section, and Daniel alluded to this a little bit the other day, but notice we have 3 forces here in this picture. And so we're looking at, I got 40 pounds, 30 pounds, and 91 pounds, and they're all pulling different directions. And if I was to draw those, as I'll do here quickly, head to tail, and notice in this drawing, they aren't drawn to scale. Like 90 pounds is 3 times as strong as 30 pounds. And so if I draw the 40 pounder that long, then I would have to head to tail draw the 30 pounder, shorter than that, and that's horizontal. And then this last one would be 3 times as long as that. So I'm drawing, and notice as I said the other day, I'm doing this in no particular order. The 90 pounder is going that direction. Do you understand, or does the logic make sense to you? That, because we're just trying to figure out, your job as an engineer is, if you have all these forces pulling on this, you got to understand what that's going to do. And so you can fix it. Can you appreciate if all of that is pulling, then it wants to sort of rip that off the ceiling right there? And rather than trying to manage all 3 forces, that's very confusing, or remember, there could be more. You've got to turn all of that into, well, this resultant, this result, or as engineers call it, a resultant. And now I can just say, oh, there's only 1 force. And would you agree my picture is to scale enough, even though I sketched it, that I can actually tell what's going to happen? Overall, this is pulling down on that ring. But can you appreciate, to solve for that red one, I don't have a triangle anymore. We have law of sines and law of cosines for triangles, but this is no longer a triangle. It's some random 4-sided quadrilateral. And so if you were going to do this using law of sines and law of cosines, you'd actually have to split this into 2 triangles and do law of sines and law of cosines twice. And that's just very inefficient. Does it work? Absolutely. If you got lots of time in your hands, go try to do it that way. But it's way more efficient to do what Daniel was hinting at the other day, which is just resolve these into their components. Like 40 pounds we see is pulling off at some angle. And we'll notice in this problem, they're not actually giving us angles. They didn't say what degree it was. They're giving us like a ratio. And that's oftentimes the case in real engineering drawings, because angles are fairly inefficient, and they're also kind of hard to read. Like if you go out on a job site, you have a giant protractor to locate that. Whereas if this says measure over 3 and up 4, then you can actually locate that angle just with a tape measure. Do you see the logic in that? And notice it doesn't even say what the units are. Is it over 3 inches and up 4 inches? Is it over 3 meters and up 4 meters? Doesn't make any difference. No matter what you measure with, that'll produce that. It'll produce the angle, no matter kind of what ratio you actually pick. And so this is a common way to describe an angle using a ratio. And so this says determine the magnitude of the resultant force and its direction, just like the other problem did, but this time there's 3 forces. And so we're going to do this using, well, I think it was 2.4 techniques, which is resolving it into its X and Y components. And so let's take a stab at that right now and see what we can do. So this is really a 2.4 question, and you have assignment questions about that. And so this is basically, as I said, resolving the forces into their X and Y components. And this is just so easy. Like, this is so much easier than the law of sines and law of cosine stuff we did the other day. And as I said, we don't even have to, we can handle 3 and 4 and 5 different forces using this logic. And so really cool stuff. So let's see, how are we going to write this? Well, let's look at that 40 pounder first. Notice they gave us the hypotenuse. Why didn't they just give us the 3 and the 4 for that? They gave us the hypotenuse too. They gave us 5. And basically what that's telling us is 3/5 of this is X. not 3/4, but 3 out of 5. In other words, if you wanted to find that angle right there, couldn't you do cosine of the angle is 3/5 and figure out what that angle is? You're more than welcome to change it to an angle if that makes more sense to you. But you're actually getting the hypotenuse involved. So as a ratio, 3/5 of it is going in the x direction, and 4/5 of it is going in the y direction. Remember, cosine of an angle is adjacent over hypotenuse. Like cosine includes hypotenuse. That's why we're including it here. So if that's the case, then for the 40-pounder, I could take 40 times 3/5 to get the x component. Let's see, 40 divided by 5 is 8. 8 times 3 is 24. And notice this is in pounds, and so that'd be 24 pounds is the x component of that. And 40 times 4/5 would then be 32 pounds. So I'm sort of going to say, I don't need 40. I need 24 and 32. Now I want you to stare at this for just a second. If you did 24 pounds in this direction and 32 pounds in that direction, what happens since that's at 90-degree angles? What if you did Pythagorean theorem on 24 and 32? What do you think you're going to get for a hypotenuse? Do it on your calculator if you're not sure. I'm doing it. 24 squared plus 32 squared, square rooted. What am I going to get?
40.
You're going to get 40. I mean, do you see how it's working? 40 is at an angle. And we need to know how much of that is going in the x and how much it's going in the y. And so apparently it worked. Do you see why I included the hypotenuse in that ratio down there? Because we're trying to get the hypotenuse involved. The hypotenuse is 40, and that's actually the direction the force is actually going. So sort of 3/5 of 40 is going in the x direction, and 4/5 of it is going in the y direction. Now, how do you write that down? There's all kinds of ways to write it. I'm going to call this force 1. There's nothing in the picture that would give me a name already, so I'm just going to call them force 1, force 2, and force 3. Here's how you could say it. You could say force 1 is equal to, and did you see this in physics? I actually don't know the answer to this. Did you write vectors in this way in physics? Just like in math, you put the x first and you put the y second. Have you ever seen that form for vectors?
Oh, yeah.
Yeah, we use them a lot in physics.
So if you're comfortable with that already, you're done. There's how you write it. You can also write it as 24, well, I'm going to erase this, but you might think 24x plus 32y. Because if you put a plus sign, now it's not so obvious which one is x and which one is y. In this book, you're going to see it as I and j. Now that's a little annoying because it's like, now I got to memorize that I is x and j is y when I already know x is x and y is y. Have you ever seen that before? I don't know, so answer that. Have you seen that?
Yeah, I've seen it before, but I think not as much maybe as the other one.
Yeah, so this is kind of your choice. I mean, you gotta, either way, I don't care, like pick one. And I'm gonna probably go back and forth. I'll probably do both.
Can we write it as brackets vertically? Is that an option?
Yeah,
I like
yeah.
that way.
Or you may have seen it written like this, 24 and 32. That you won't see in the book. You'll see the first two in the book, I think, and I think predominantly you're going to see I and J in the book, but those are all fine. The key is just keep track of them. One is X and one is Y, and you can't screw it up. If you get them backwards, not good, right? So I don't care what you do as far as your work. I'm probably going to mix it up a little bit. I never ran into the vertical version in the way I was taught, and so that just isn't a part of my logic and part of my thinking. Also, keep in mind, we're going to go 3 dimensions, and we're going to do that right after we do this problem. Like, we got to be able to do 3D. So we're going to have 3 components, an X, a Y, and a Z. So we'll have either these chevron brackets with 3 numbers, or we'll have I, J, and K. K will be our Z component, or a vertical with 3 numbers in it. Let me see, I'm looking at my notes real quick. In my notes, I actually am using I, J, and K some places. Okay, so anyway, we resolved force 1 into its components. Now let's go resolve 30 into its components. Why is 30 really easy? What I'm calling force 2. Why is it really easy? I know it's obvious, but somebody tell us, why is it easy?
You just got a y value in one direction, or no, it would be x, but you just got.
That's right. Like it's not pointing.
You already have.
If something's pointing straight up or straight down or straight left or straight right, then it only has an X or a Y component. This only has an X component. And notice, by the way, it's right, which is positive. We got to think about that. So this one's really easy. So you could say force 2 is 30 to the right positive and nothing up and down. It's not going up and down at all. It has no X or Y component. So again, you could say 30I plus, and you could say nothing, just call it 30I, but it might be good to put 0J, just making sure you realize, oh, I didn't forget it. It's just, it's actually 0. And lastly, I'm going to give you a second to do this yourself ahead of me. Scratch paper. What's that 91 pounds or force 3? Beautiful stuff. Well, the horizontal or X component, since the horizontal is 5 and the hypotenuse is 13, would be 5/13 of 91. Maybe you wonder, why did they pick such a weird force of 91? It's really weird, but notice 91 divides by 13. So they were actually trying to make it nice for us. 91 divided by 13 is actually 7, and 7 times 5 is 35. So you get 35 pounds of force in the X direction. The vertical component or the Y component, notice it's almost vertical. So not very much of it is horizontal. It's not pulling very hard to the right, only 35 pounds to the right, but it's almost pulling straight down. So our answer to this is going to be really close to 91. So if I take the vertical component, 12/13 times 91, 91 divided by 13 is 7, 7 times 12 is 84. I get 84 pounds. So do you see what I mean? It's mostly pulling down. So most of the 91 pounds is going down. But notice 84 plus 35 is not 91. You're not adding these. It's Pythagorean theorem that relates them. It's a right triangle. What's wrong with what I'm writing here? Force 3 is 35, 84. What's wrong with that? It's wrong. Do you know what's wrong?
It doesn't have any labels.
Pounds is good. So I'm being a little bit lazy there. I should say pounds, but it's still wrong.
I think Landon wrote in the chat what was wrong with it.
Yeah, I think I saw a chat pop up, but I didn't look at it. What did Landon say? Landon said it should be negative. Exactly right. Because it's down. And so you got to pay attention to that. That's an easy thing to overlook. But can you appreciate if you say, you know, positive 35 and positive 84, that's up. Like this isn't up. That's very important. You wouldn't want to get that wrong in the real world. And so notice you got to divine that yourself from the picture. There's nothing mathematically that's going to tell you that. They didn't write negative 12 down there, and it would be dumb to write negative 12 in the original ratio that they gave. And so that's got to be negative. And so what do I do then, my friends, to get the resultant for this? What do you think I'm going to do to get the resultant? Resultant. I have two ants. That's dumb. What am I going to do to get the resultant? Why is this really cool? No law of sines and law of cosines.
Add them all up.
Add them up. Exactly. And did you do some of this in physics already?
Oh, yeah.
Yeah.
Oh, yeah.
This isn't new, right? So for the horizontal, and I'll just write it this way. So for the horizontal x's, I have 24 plus 30 plus 35. Notice they're all positive, and the picture shows that. They're all going to the right. So if I add all of those up, what do I get? 65, 89. I get 89 pounds effectively to the right. What do I get if I kind of add up the vertical or the y components? I get 32, which is positive, 0, which is signless, and I get 84, which is negative. And so I get negative 52 for that. So I could say force resultant is 89 comma negative 52. That'd be true. And I could be done. That's the answer. That's the answer of the resultant for what this vector is. Is that what the question asked us to do? Am I done as far as what the book happened to be asking? No, because it said it wanted the magnitude and the direction, like as an angle. Is this easy for you because of how much math you've had? I sure hope so. In the sense that you say, well, here's what it would look like. There's the 89. And trying to draw this to scale, if I draw that as 89, 52 would be shorter than that. There's the 52, and I went down. And so isn't this then the resultant of that? Isn't that the, I'm just going to say result for short. And you should just look at that and go, oh, I see how to get the angle. I see how to get the hypotenuse. That's just basic math that I know. I know how to get theta. I don't need any formulas for this. I know that the tangent of theta is opposite over adjacent. Notice I'm using my picture. I didn't put a negative in there. I'm just using my picture. So if I say second tangent of 52 divided by 89, I get 30.296 degrees. Theta is approximately 30.296 degrees. And so the picture tells me it's down. If you wanted to write it, you would not just be able to say 30 degrees. You'd have to draw a picture. The picture would be fine because then it would tell you it's down. You could say negative 30.29 degrees. Of course, again, as I said the other day, what's the book going to say for the answer to this based on our rounding strategy?
It would just be 30.3.
30.3, measured clockwise from the positive x-axis. So they're telling us clockwise means go that way. So because of that work, because of those words, I can actually just say 30.3. You see what I'm saying? Since the clockwise was in there. But in a sense, I think a better answer would be to sort of draw this little picture right here and say theta is approximately 30.3. Say approximately, not, I don't care, but say approximately. Tell people you rounded off. Tell yourself, hey, I rounded that to the 10th place. This is the direction. That's the result of all three of those forces. Can you appreciate this technique doesn't care if there's 50 forces because all you have to do is add all the x's. So this is way easier than geometry. That's kind of the point. Again, that's hopefully not brand new to you. Hypotenuse, what am I going to do to get the magnitude? Oh, that's just Pythagorean theorem. So that's easy. The magnitude would be equal to the square root of, notice the square root does not, or the square does not care whether that 52 is negative or positive, since when I square a negative, it's going to be positive anyway. So square root of 89 squared plus 52 squared. This isn't hard. 103.07. 0776. And so again, according to the standard of the book, that's going to be 103. And again, you're going to be wrong in this class. I don't really have any choice but to take points off in this class if you don't say pounds. There's two standard ways of measuring weight and mass. It would be kilograms is the standard for for metric, and this is again in chapter 1. Kilograms is a standard weight, not grams, not micrograms, not megagrams, kilograms. Or in pounds.
Technically, isn't kilograms a mass? Wouldn't we have to use newtons for forces and weights?
You are exactly right. Because this is a weight or a, yeah, so that'd be a mass. If I said 103 kilograms, that'd be a mass. If it was a force, I'd have to multiply that by the acceleration of gravity to actually turn it into a force to make it newtons. And so you're exactly right. Had these forces would have been listed in newtons because they're forces, not masses. So that's a good point you make. So does it make sense? As far as this problem goes, I'm done. But does it make sense in the real world? You're not done. Now you know what you need to know to go design that connection up there so it doesn't tear off the ceiling. Like you're just getting started as an engineer because you got to make this work. But we're done as far as learning statics. We found the resultant of all those forces. Not hard. You happy? You got to interrupt, or I'm going to assume you get this. So let's take a look now at a 2.6 question, which is where we go 3D. So we're going to look at question 2.8 in your book. This is in your book. Error. It says error. That's not good. Why does it say error? Why that says error. I'll do something insane and try the same thing that I just did and hope for a different result. Seems like it's working for that. That's good. So it's not the problem. Let's try this again. So it doesn't like 280. Pardon me for a second while I try to send that note over there to Google Drive. 1 second. Nothing wrong with it there. Somehow my wife has managed to take this over and her stuff is all in here, so it's looking in the wrong places. Okay, sorry about that. You see this, correct? Everything's good? So I'm gonna give you a second to stare at this. It's the same problem, isn't it? Don't we just have forces pulling on something? But what's different about it?
Three-dimensional.
Three-dimension. Did you do this in physics?
I don't think we really did too much three-dimensional stuff in physics.
The good thing is this any harder? No, we just got to do it in 3 dimensions. We just got to add x's with x's, y's with y's, and now z's with z's. And you can appreciate how hard would this be to draw vectors head to tail if we had to draw them 3D. Now, I suppose you could do it if you had a 3D drawing program, but like, you know, your head explodes. But this is super easy as long as we break things into their x and y components. However, you're trying to look at a 3-dimensional drawing, a 2-dimensional drawing of a 3-dimensional reality here. That's not good. So force 1. What direction is that going? Like, where is force 1 pointing? What's that 25 degrees and 35 degrees? What the heck is that? Can you tell what they mean by that? I had a hard time with this when I first looked at it, so I'm trying to give you some think time here.
Is that maybe going like 25 degrees from y to x, and after it goes down 35? No,
That's exactly what it's doing. It's the 25 is telling you where it is in the XY plane. So it's going from the y-axis toward the x-axis and staying in the XY plane, and then down 35 degrees. That's hard to see. Aaliyah? Turn your mic on. Go ahead.
If you look at the blues, the different shades, the line that like the end of the triangle, it's kind of parallel with X for the 25 degrees and parallel with Z for the 35 degrees.
Very good.
But that is tricky to spot.
So tricky, so tricky. Looking at, well, let me give you a quick example. Would you agree I just drew a box right there? It's almost hard for you to see it as anything but a box because it's a fairly decent sketch of 3D, but to fake the eye out in the real world, isn't that angle right there 90 degrees? But I couldn't draw it 90 because when you look at it, when you look at a box from a different angle, you're not seeing 90. So that this is really hard, and you gotta get used to. You got to get used to this. And so when I look at this picture, I sort of feel like there's the right angle right there, but do you agree that's not the right angle? And if you get this wrong, you're going to get this problem wrong. That looks like the 90 to me, but it's not. Take a look, and what Aaliyah said is bang on the money. So let's take a look at this. Would you agree that, you know, this is the y-axis, but would you agree that that's parallel to the x-axis over there? Therefore, that's the 90-degree angle. Now, the drawing is perfect, but remember, you're trying to look at 3D. And so that's tricky. So the 90 is actually sitting over there. So we have a right triangle that gets us location in the XY plane. And now let's look at the next right triangle that's down here. Do you see the right triangle? Do you see where the 90-degree angle is? Where's the 90-degree angle? It's right there. Now, fortunately, when the book gives you the location of something via, and I think this is called azimuth zenith or something. I forgot the name of this, but it's like, it's just like if I said, hey, there's a star, there's a really cool star in the sky, and you look up there and you're like, dude, there's 50 million stars. Which one are you looking at? How do I tell you which way to look? Well, I could say, okay, face north and turn in your compass, you know, turn like 40 degrees and now look up 50 degrees and there's the star. That's what this is doing. It's saying orient yourself in one plane and then look up or down from there. This is a great way to describe it. You can't describe 3D any other way. Well, there's a second way in this problem. We'll get there in a second. So let's see if we can figure this out. Of those right triangles, notice we know some angles. We know 25 and 35. Do I know any lengths? Say yes, or tell me what it is, or no.
You know, the 250 newtons, the F1.
Yeah, we got 250, which is the hypotenuse. It's always the hypotenuse. It's the hypotenuse. And notice, like Daniel mentioned a minute ago, notice the forces this time are metric. They're in newtons. We know the hypotenuse of that right triangle. So armed with that knowledge, can't we come up with this z direction right here then? Is that a sine, cosine, or a tangent problem? Come on, time's a wasting. Hit space bar, blurt it out. You're wasting your time. Or do you not know? I'm not sure.
So that would be tangent. We're to get the. So you're trying to get the z on the other side.
Yeah, I'm trying to get the z.
That the z length of it. Okay, yeah, that would have to be.
So that's the z is opposite. Do you agree that's opposite? What's 250?
Or no, that would have to be. No, it had to be sine. That would be hypotenuse. Yeah, sine.
So, TOA. Yeah, this is opposite and hypotenuse. It's sine. So I could say the sine of 35 degrees equals opposite over hypotenuse. So if I take 250 times the sine of 35 degrees, I get 143.39. What should I write down? Listen carefully to this. What should I write down? 143.39. What should I write down as the answer to this if I was writing it down?
3 decimal places, just your 143.
143. But we're not done yet. We're going to use it for other calculations. So don't put it off now. Carry it out further. Call it at least 143.4. Because it's 394, I'm going to just leave it at 39. That's close enough. But don't round too soon. Remember that logic? So I found z. So I actually know for F1, I already know the z component. And notice it's down, so I got to make it negative, which again is very hard to determine from the picture until you get some practice looking at this. So there's my z component. Would you agree, if I look back at this picture, let's see, would you agree this is your x component? Because isn't that going in the x direction over here? It's parallel to the x direction, so that's the x. And this is the y. How am I going to get those? I don't know anything about the red triangle. I know 25 degrees, but I don't know any lengths. How am I going to figure this out? Aaliyah, just talk. Raise your hand.
Find find the length of the rest of that blue triangle.
Exactly. That's exactly right. That blue triangle up there, I'm going to call this T for no good reason. T. Couldn't I go back to that blue triangle and say that the cosine of 35 degrees is adjacent over hypotenuse in the blue triangle? So 250 times the cosine of 35 is 204.788. So I'm going to call it 244. I'm sorry, 204. 204.79. I'm carrying them out 2 places right now. Now notice what was one of the legs in the blue triangle becomes the hypotenuse in the red triangle. And again, it's very hard to see that T length is the hypotenuse. It doesn't look like it, does it? Most people are going to think what I called Y is the hypotenuse if you just look at this and don't really think carefully about what Aaliyah said about parallel and stuff. And so now I know the hypotenuse. So you really need to draw the right triangle in there, or draw the right angle like I did. So now you can figure out X and Y. So let's see. And by the way, if you need to redraw the triangle, like draw it facing you, it's drawn in a perspective view right now. Redraw it if you need to. I'm not going to, in the interest of time. But since T is the hypotenuse, couldn't I say that the cosine of 25 degrees is adjacent Y over hypotenuse 204.79? This is why I didn't round that to 205, because I'm using it to do something else. So 204.79 times the cosine of 25 tells me that y is approximately 185.60. So I found my z component, I found my y component, and lastly x. So I could say the sine of 25 is equal to opposite over hypotenuse. And if I multiply the sine of 25 times 204.79, I get 86.55. And so now I have all the components. Now, you're done right now. Like there's nothing, there they are. I mean, I wrote X, Y, and Z. So it's like, I'm not going to screw up which one is which. Is anything wrong with any of those answers? The answer is yes. What's wrong with one of those answers?
Z should be negative because it's going down.
Yeah. Now here's something that's kind of tricky that's not obvious. Notice the X is right here, which means that direction is positive X. Remember, this is three-dimensional, so it's totally hard to picture where you're going. Which way is positive? It's toward the letter. So that's positive X, this is positive Y, and that's positive Z. Now up feels like positive and down feels like negative, but the other ones, what makes them positive and negative? And so to get to our vector, we went positive Y. Watch this, watch what I'm doing right now. Don't write for a second if you are. Notice from 0, 0, I first went Y. Hey, that's going in the positive direction. And then I went this way in X. Hey, that's in the positive direction. And then I went down. And finally it was like, oh, that's the direction I'm going. I mean, it's like I had to establish this point in order to be able to draw that arrow. So the Y coordinate and the X coordinate are positive, but that Z coordinate's actually negative. Again, I'm going to get this wrong if I don't recognize that. And so I'm done. Now I could go back and say force 1, this is the best thing to do, although it's kind of a waste of time. Go back and say 86.55, comma, y 185.60, comma, negative 143.39. And even better would be after this to say n for newtons. Tell people that those are newtons. If I'm done, if all it says is what's force 1, break force 1 into its components, then that's the perfect answer because I didn't leave the units off. You don't have to put newtons in every one of them, just put newtons at the end. But again, what I'm trying to do is resolve two of these, two resultant. I'm trying to resolve two different forces pulling on this. And so I got to get a second one, and then I got to add them together. So force 1 is done. I'm very excited. Let's go get the second force. Notice in this problem, they actually labeled them for us, force 1 and force 2. Stare for a second at force 2. Where is that pointing? It's
in the negative X direction, it looks like.
Yeah, you think it's in the negative X direction. Why do you think that? You're right, Landon. Why do you think that?
Because presumably it's hiding the x-axis line.
Well, we can see that's 120 degrees from positive X.
The 120 is the key to it. Had it been 90, does it make sense it would have been in the ZY plane? But it went on past that. So I think you're right. And now again, what's tricky about it is it's not laying on the x-axis, which I think was what Landon might have been thinking, but it could be. It's the angles that tell us it isn't laying on that because that 120 would have to be 180 for it to be laying on the x-axis. Does that make sense? Super hard to picture. Like, how are you going to do this? I can't draw any right triangles here. Do you agree? Like, it's super hard to picture this. Where is this thing actually pointing? So it's 60 degrees from Z down to it, but it's 45 from Y. How come that doesn't add up to 90?
Because it's not in the YZ plane, it's past it.
Exactly, Daniel. It's not in the YZ plane. It's actually beyond it. It's actually over in the negative X. You see, you got to work at this to even picture which way it's going. And once you get done picturing it, you still feel like, nah, I don't know what to do. Now, fortunately, I'm going to share a different screen for a second here. If you look at the note sheet that I gave you online and that you should have printed, and I really do mean printed. Where are you, note sheet? You must be in tests, test notes. So I posted this for you at the website, and I mentioned to you I was going to be explaining this today. Notice this says a Cartesian vector. Cartesian, what's the deal with Cartesian? That's Rene Descartes, who invented the idea of a number that has two components being visualized as a graph. So the Cartesian coordinate system is the X, Y, except for it's bigger than that. It's X and Y and Z, and this may be the first class where you've ever went into the Z axis. If you take Calc 4, you'll go into the Z axis with regular math. But notice a Cartesian vector is an X component, a Y component, and a Z component. So this is a formula that allows you to kind of deal with 3 dimensions. And what does it say? The magnitude of A, the magnitude of vector, notice there's a little vector symbol over A, so you know it's an arrow with a magnitude and a direction. And another way to say magnitude is a couple of lines around it. Have you seen that before? I don't think you have, am I right? I don't think you've seen that before. That's a way to say, hey, I'd like the magnitude. Mathematicians, physicists are notoriously lazy. They don't want to write the word magnitude, so let's come up with a symbol for it. So a double line, not a single line, because then it looks like absolute value. So a double line. And notice, what do you notice over here? It's just 3-dimensional Pythagorean theorem. If you take all 3 of the components and square them and add them together and square root them, then you'll get the magnitude. Hey, that's interesting. Remember this problem a second ago? What's going to happen if I square, you don't see this anymore, but remember 143, 185, and 86? If you square all those and add them together, guess what? You're going to get 250 newtons. You might try that on your calculator. Like, that's kind of a test to make sure you didn't screw this all up. So it's 3-dimensional Pythagorean theorem. It still works. That's the thing that's really cool. More importantly for us, what do you notice down here that's extremely helpful for us? How do you get the AX component, the X component of it? Well, you take the inverse cosine of the component divided by the magnitude. So it's cosine. Cosine will do it. Like, I don't have to draw the right triangle. I just get to use cosine. So what this is saying is, another way to write this is the cosine of the A angle, alpha. Alpha is the one that goes with X. Beta is the one that goes with Y. And gamma, is that right? Gamma? Yeah, I think that's gamma. Gamma is the one that goes with Z, as far as this note sheet's concerned. So the cosine of the angle is equal to, well, isn't this what we just looked at a second ago? It's like the X component divided by the hypotenuse. A second ago, didn't we go 3/5 and 4/5? It's the same exact thing. It's just cosine. Cosine will give you the adjacent side, and the adjacent side will be the X or the Y or the Z. That's what this note sheet is saying. So basically what I'm saying is this process is automated for us a little bit, thanks to well, mathematicians spending some time in 3 dimensions. So this is easy then. This is saying, let's see, what is my hypotenuse is 400. So there's my hypotenuse. And let's see, for X, I'm at 120 degrees. So all I have to do then is say the cosine of alpha is equal to the X component. Let's see, I'm going to say, since it's F and not A, I'm going to say F of X divided by 400. Except for the X version of this had an angle of 120 degrees. It's the same thing we were just doing. It's just 3D. So this is saying my force X. And I should, by the way, not just say force X because I already have a force X from the previous problem. I should be a little more careful and even say force 2X. You see what I'm saying? Am I going to mark you wrong on a test for that? No. Notice it's here under the force 2 calculations. And so if you want to be lazy and just say force X, good for you. There's nothing wrong with that. So if I take 400 times the cosine of 120 degrees, notice that takes care of, remember cosine of 120 might be negative. I just got negative 200. That's interesting. So force 2 in the x direction, actually I can say equals because it came out perfect, is negative 200 newtons. And I won't write that down right now. What does the negative tell me that we reasoned out just a minute ago? It tells me it's actually not pointing in this positive direction. It's actually pointing in the other direction. Notice the negative took care of itself. That's actually kind of cool. It turns out that these are easier. This blue and red triangle stuff, harder. I can just use a formula when I'm given all three of the angles. That's kind of the key. So this blue and red one is called the transverse azimuth kind of method, if you will. You don't need to know that. But this coordinate direction angles, your book will call this coordinate direction angles. I'm going to write that down just so that you kind of can see the word. Whoops. Coordinate direction angles. In other words, it gave us three angles. It takes three angles to define exactly which direction you're going here. So this method is actually easier. Okay, well, let's just keep going then. So the cosine of the y coordinate was beta, and that equals force 2 in the y direction, also divided by the hypotenuse of 400. But what was the y angle? I don't know, I forgot. I got to go look. From the y-axis, notice the arrowheads. It's pointing at the y-axis, and it's pointing at the vector. Oh, it's 45 degrees from the y-axis. It's pointing at the y-axis. So that's 45 degrees. Okay, then I just take 400 times the cosine of 45. And I get 282. I got to round it. Force 2 in the y direction, I'm getting approximately 282.84. And I really haven't read the problem yet, so I don't know how far to round this. So I'm just carrying it to there. And again, I get positive, which means it's pointing toward the positive y. Don't you agree that that was pointing toward the positive y? That should have came out positive. The cool thing about coordinate direction angles is the positives and negatives happen automatically. Like you don't have to think like we did in the previous section. That's really good. And finally, what's the z? Cosine of gamma is force 2 in the z direction divided by 400, and my gamma angle was, or my z angle was 60. So I switch out 60, 400 times the cosine of 60. I get a positive 200 again. That's kind of interesting. And it's exactly right. 200 newtons. So now I have my two forces resolved into their x, y, z components. And so again, I'm going to waste a second and rewrite force 2 in this form. So let's see, get them all in order. X, okay, x is negative 200, y was 282.84, z was positive 200. Yeah, it was up. And so there. And so what I'm really staring at now that I've done all this work, is I'm just staring at these two statements right here. What do I have to do to them to find the resultant? What do I have to do? Add them up. Would I care if there'd been 20 ropes pulling on this thing? No, I can add 20 numbers. Like, as crazy as it sounds to think like, what's happening? What's the result of all of this? All I got to do is add them. So result, I'm not even going to call it resultant this time. Add. X's with X's, Y with Y. So let's see, I'm going to say force, and I'm going to go back and write newtons in here because I forgot that before. Force resultant equals negative 200 plus 86.55. So 200 minus 86.55, that'd be a negative 113.45. 113. Again, I haven't really thought about rounding yet. If this is the final answer, then maybe I should be rounding, but I don't even know what the question asked. And then we got 282.84 positive for y, and 185.6 positive for y. And so they're working together. Aren't they both pulling in the y direction based on the picture? So it makes sense they're both working together, whereas they were working against each other in the x direction. One was positive, one was negative. So I get a pretty large number for this, 460 8.44. And finally, Z, I get positive 200 and negative 143. So one is pulling up and one is pulling down. Again, I saw that in the picture. So the end result is they worked against each other and there's only 56.61 remaining. And so that's newtons. And the fact that it's positive means the result of this is up. So this is the vector form of the answer. If this problem says, give us the resultant, then I'd say I'm done. I just gave you the vector form, I'm done. And that, frankly, that's a great form to leave it in because it's more descriptive. Let me try to draw that really quick just to give you a chance to think about it. Could you tell what direction that goes? I'm going to try this out. Let's see if we can pull this off. Again, because I'm interested in you learning how to think. So let's see. There's X. And there's Y. And there's Z. So there's a three-dimensional axis kind of drawn the way it was before. So now I'm going to do what this says. This says first go X negative 113. So go this way. How far is 113? I want you to answer that. How far do I go for 113?
However far as you want to go.
However far. I mean, you could actually measure it with a ruler and call it like 11.3 centimeters if you wanted to do a really good job, but draw it however far you want to go. So I'm going to stop right there. But now that I've chosen that, does it make sense I just defined what 113 looks like? And so now I've got to go in the Y direction, 468, which is like 4 times as far. Do you agree with that? So now that I've defined that as 113, I've got to now go in the Y direction. Do you understand which direction I'm about to go? How do I have to go? Aaliyah said this earlier. How do I have to go? Parallel to the Y-axis. Does that look like about 4 times as far? I'm guessing. And lastly, 56. Which way?
Parallel to positive Z.
Yep, up, parallel to positive Z. And 56 is about half of that 113, so it's about right there. So apparently that is my result. Now, when I draw that without the green lines, notice you have no idea which direction that's going. You sort of need the green lines to figure out what that means. If you take those away, then that's sort of a worthless picture. So you can picture what this is telling you. That's the resultant. And that's amazing that you can actually do this with so little effort, even though it's 3D. I mean, this is really cool, isn't it? And as an engineer, you're going to be working in 3D? Usually, like every time. You live in a 3D universe. So we got to be able to do this. Now, did I answer the question? I hope so, but what does it say? Express each force in Cartesian vector form. I did that. Then determine the resultant force. Dang. Well, no, it did. It said determine the resultant force, FR. I did. I gave it to you in vector form. Find the magnitude and coordinate direction. Dang it, I'm not done. They're saying convert it back to angles and hypotenuse. Does that make sense? In other words, how many newtons is this? Does it make sense as an engineer? You got to know that. Like how many newtons of force is this? Because remember, you're done with the problem when you find those, but can you tell these two forces are trying to tear those two screws out of the wall? Like you're not done when you calculate this. You're done with the book, but you're not done in the real world. You got to figure out how long are those screws and what are they going into? Is it wood, concrete? Like you got to make sure this doesn't tear off the wall or rip the metal in half or whatever. So we need the result and we actually need forces. We can't just stop with this vector version of the answer. So they're not wrong to ask me that. Now all I got to do is use those formulas to kind of rebuild this. What do I do to get the magnitude of force R? What do I do?
Pythagorean
Take
theorem.
the
Yeah, Pythagorean theorem. So I'm going to take, And do you see how I'm glad now because I'm not done. I'm glad that I chose to round those off a little further, because if I'd rounded those to 3 places, I'm probably going to get this wrong. Now, as far as a test, you're not going to get anything wrong. But you'd have a different answer in the back of the book. And when you see that, I don't want you to change it. Don't go back and redo your work. If the answer in the back says 119 and you have 118.87, go, I got it right. However, know why you didn't get it exactly right. You rounded too early. So in a sense, I'm glad I didn't round too early. So I'm going to take all of those numbers, square them and square them. Will you type this in your calculator while I'm writing this down so that I don't waste our time? I know negative numbers squared are positive, so I'm not even going to write the negatives in there. Somebody tell us what the answer to this is.
I got 485.299 newtons.
Cool. So what's the back of the book going to say?
Just be 485.
3 significant digits, and you're going to see newtons there. So, okay, good. Now we know how much force, and we can look at a chart and see how many screws is it going to take to keep from that ripping out of the wall. What am I going to do to get the coordinate direction angles? That's why I wrote that word down, because you could easily read that and go, I don't understand what you're asking me to do. What do I do to get the coordinate direction angles?
Go back to the formula that we used for the second vector.
Yep. So the alpha is equal to the inverse cosine of the x coordinate. Notice you need the negatives. Why do you need the negatives? Because the negative is going to change the direction that this goes. Like, I really need that negative. Is 485 okay? No. Because I'm calculating, and so it's rounded a little too early. So maybe I'll come back and put the 0.3 in there. Again, if you're wrong by 0.1 degrees, do I care? Change your assignment? No, just recognize, oops, like make sure you know why. Because in the real world, you need to get this right to the 10th place. Don't round too early. So if I say inverse cosine, make sure my note page is speaking to you, because you get that on the test, but you don't get to write your own notes on top of it. If there's something I said that you think could be said more clearly, tell me and we'll change the notes. We're working on that together. I got that alpha is 103.5. 103.5. That's actually 104. That's the answer I would see in the back, because it's 3 decimal places or 3 significant digits. Notice the fact that it says 103.5. That was darn close. That was darn close. It's right on the line between 103 and 104. And so if I rounded this at all wrong, the answer in the back could actually be 103. Again, I don't really care, but it's just kind of cool to point out. The X angle. And so I'm going to write X down there. You don't need to, but you're not used to these designations for X, like X, Y, and Z you get, but alpha, beta, gamma, like you've never seen those equated to X, Y, and Z. So I'm just going to throw a little X down there for the notes to say that's the angle from the X axis up to where that is. Now, does that look right? I drew the picture a second ago. Could you draw 104 in that picture right there? Do you understand where that goes? It's straight from here. What plane is that arc that I just drew in? Is it in the XZ plane, the XY plane, or the ZY plane?
It's in none of them. It's that X and the FR plane vector.
Nice job. I asked you in a way to even trick you and landed was not tricked. It's not in any of those planes. It's in some weird plane. And so by itself, 104 is not enough to tell you where this thing is going. We need it in all the other planes too. Notice it's positive. That's interesting. So then what about beta? Well, we're just grinding now. Inverse cosine of the X coordinate, which was 468.44, 468.44 divided by 485.3. So when I type that into my calculator, I get, see, I wrote this down somewhere earlier, so I'm not going to waste the time. I got 15.1 degrees for that. So beta, which I'm going to note is in the y direction, is 15.1 degrees. Notice this one actually carried out. The first one looks like it's rounded to the whole number, but the second one looks like it's rounded accurate to the 10th. Remember, 3 significant digits, doesn't matter where they are. Does that look like 15 degrees from the y-axis? Notice it does. Like that's a pretty small angle. Did it look like way more than 90 degrees from the x-axis? Uh-huh. That does look pretty small. Does it look to you like less than 90 degrees from the z-axis? I hope we get an answer less than 90 degrees because it does look that way to me. So gamma is the inverse cosine of the y coordinate, which is 56.61, also divided by the hypotenuse, 485.3. You get gamma, which I'm reminding myself is in the z direction, is 83.3 degrees. And yep, less than 90. Now again, did you expect it to be 15 minus 90, 75 degrees? No, because it's not in the zy plane. Our vector here is not in the zy plane, so I don't expect these to add up to 90 degrees. So 83.3 degrees. So now I know exactly which direction it's pointing. But again, I can't picture it. I'm really good at 3D stuff and I can't picture that. It's really hard. I got to think, I got to work at it. So resolving things into their X, Y, and now Z components makes this stuff totally easy. How's your brain? You all right? Smoke coming out of it? You okay?
I have a question. You mentioned that it was weird from X to be positive 104 degrees. Does that make sense now? Or
yeah, so interestingly, this method will always give a positive answer. It'll never give you, you'll always have positive angles. Because notice it's hard to tell which way is negative. Like, I don't really understand where I am in 3D. What's negative? There is a thing called the right-hand rule that we'll get into a little bit later, but negatives and positives matter. Like if we went the wrong direction, 104, that would be fatal. Like that makes the bridge fall down. But the cool thing is we're going to get positive numbers here every single time. So that's kind of good. Okay. We got to look at.
Oh, before we move on, actually, I've got a quick question. That was a kind of a really unusual set of axes. Like, it feels like my brain is telling me that X and Y should have been swapped there because it's not right-handed coordinates. It's not left-handed coordinates. It's kind of this weird.
Good job. And that makes this really difficult. Generally speaking, the way 3D is modeled, because all we have is two-dimensional drawings, is the XY plane is the floor. But we have to look at it in a different direction. We can't look straight down on the floor because otherwise the z-axis would be pointing right at us and we wouldn't be able to see it. It's just like the box I just drew, essentially. So yeah, I mean, what you need to do in these pictures is just rely on the figure. In other words, hey, look, there's X. Hey, look, there's Y. Hey, look, there's Z. There's the positives. You don't have to draw them all the same direction. Every drawing you see in these was not all going to be pointing the same exact direction. But visualize, and this problem helps, I think, because it's a flagpole. X, Y is the ground and Z is coming up. But if I'm going to see all of these measurements they're giving us, then I'm going to have to draw it at some weird perspective. Would you agree this angle down here, although in real life it's 90, they actually drew it as like 120 degrees. That's what makes you actually think you're seeing 3D. So you're right, Landon. It doesn't actually make any difference, and you actually might have a way that it sort of makes more sense to you. But you don't have to care as long as you stare, as long as somebody has labeled them X, Y, and Z so that you know which direction and what's positive, no big deal. Now, why is this different than the last question? This is still the same thing. You have these two forces pulling down on this flagpole, but why is this different than the last problem? I haven't even read the question, but what's different about it?
It shows us lots of length and no.
Yeah, it's giving you the location of the direction based on lengths. just like the problem I introduced the discussion today with. It's given it based on lengths, not based on angles. And frankly, that's good news for you. This is easier. You're told which way it's going based on lengths, not angles. But you do have to stare very carefully at all those 2s and 3s and 6s in order not to screw this up. And so let's wade into it. Now, what is it asking? Let's see. It says here that, oh, thank God, force B is 560. Notice they call them B and C. So this one is, let's see, I don't like pink. Goodbye, pink. Let's go red. This one, force B is 560, and the other one is 700. Is that going to pull the flagpole over? I mean, those are pulling on it, right? Is the flagpole going to stay static? Or is this going to tear the flagpole down?
I mean, depends on the mounting, right?
Depends on the mounting. That'd be your job as an engineer. If you're going to pull on that for whatever reason, you better have those bolts down there mounted in such a way that they don't tear out of the ground. In order to do that, we're going to have to find the resultant of these two forces, and then we can, figure out how many bolts and what size they need to be and what they're screwed into and all that stuff. So it's the same problem we just did, two different forces, but we're just given their direction in a different way. We don't have a lot of time here, so let's see if we can wade into this. So let's see, B comes before C, so I'm going to do force B first. Notice I'm teaching you how to be organized. As an engineer, don't just have your work all over the place, like organized. Notice I put a little cloud around that just so that it's like, this is one of the things you want to look at. And I'm sort of reserving some space here. Later on, I'll probably like make a line and then we'll work on force C or something, but it's like, be organized for your sake and mine when I'm looking at your test. If you get this wrong on a test, am I going to be able to read your work well enough to see if your mistake was just an accident versus you don't have any idea what you're doing? If I can't, if its work is terrible, I'm going to get tired of looking and give up. So I'm trying to model good behavior in terms of what an engineer's work should look like. I don't care how you designate force B, make it bold, big, draw a circle around it, draw a square, but just something that says this is my force B work. Now let's see, let's stare at force B. Would you agree that that 2 right there is in the X direction? See how the arrowhead points that way and it's parallel to the X axis? So it's 2 in the X direction, 3 in the Y, but notice it's negative Y. It's 3 backwards in Y. And then, let's see, what about that 6? This is kind of confusing. That 6 is, again, parallel to the Z axis. So let's see, if I just kind of write this down, X is 2, Y is 3, Z is 6. Again, I got to be careful with negatives. Which ones of those are negative? This is really tricky. It's not tricky ultimately, but you got to think.
Well, why? But would C also be negative?
Why are you thinking that? You're actually right. Why are you thinking that?
Since from A to B, it's heading in the negative Z direction.
That's exactly right. See how this vector has an arrowhead? It's actually going from A to B. So A is actually kind of the origin in a sense here. It's coming from A. So is it going positively in the X from A? Since A is kind of on this axis right here. Yeah, that's actually a positive 2. From A, it's going a negative 3 and it's going down. So it'd be a negative 6. Now, unlike the problem I started with the class, they actually, when we started class today, they gave us the hypotenuse. Remember how it was 3, 4, and they told us 5 was the hypotenuse? Do we know the hypotenuse here as a length? Remember those 3s and 6s and 2s are meters. Do we know how long AB is as a guy wire? Do we know the length of that hypotenuse? We do not. We do not know that length. So I've got to Pythagorean theorem my way into that answer. So I've got to go 2 squared plus 3 squared plus 6 squared. Notice I'm squaring them, so I don't care about negatives. Miraculously, you get 7 because they were really nice to us. You get 7 for the hypotenuse. So that means the length of AB is actually 7. Not 7 pounds or 7 newtons, it's 7 meters. So I'm going to go back and write meters on all of those. These are all meters. And so now what I have is a way to, well, get the proportion of 560 that's going in all the different directions. Does that make sense? So I could say force B then is equal to, well, 560 multiplied by the X proportion is 2/7. The Y proportion is -3/7, and the Z proportion is -6/7. So just like we did at this problem at the start of the day, if I multiply 560 times those components, then that'll break 560 into its component parts. And notice again, they were really nice. 560 divides by 7. They purposely chose 560. That wasn't random. 560 divided by 7 is 80, and 80 times 2 is 160, I think. So force B then is actually 160. 560 divided by 7 is 8. This would be -240. And 6 times 80 is 480. So I think it's this. And again, it's good practice to say newtons on the end of this. That's actually force B broken into its component parts. What can I do to check my work? Because there's a lot of dumb things I could do wrong here. What can I do to check this just to make sure?
Just plug everything back into Pythagorean theorem, and then you find your,
Yeah.
if you get 560, then you know you did it right.
Exactly right. And that might be a good thing if I was on a test, or if you're an engineer and you're actually going to build something. Like, you can't be wrong as an engineer. Does that make sense? Like, hey, 95%, I got an A. No, that's how you lose your job. That's how the bridge falls down. So cool. All right, I'm done. In my case, since I have colors to choose from, maybe I don't need to draw anything else. I'm just going to change colors. Now I'm going to start working on C. Notice C also is 2, 3, and 6. So if I Pythagorean theorem 2, 3, and 6, I'm also going to get that AC is 7 meters, since it's the same exact dimensions, so the same fractions. So is force C then equal to, oops, give myself room. Do I take 700 and then multiply by, let's see, what are the fractions? Which one is which? It looks like 3 is parallel to X, so 3/7, and 2 is parallel to Y, so Y is the 2, and Z is the 6. What have I not thought about that I still need to think about?
Positive and negative signs.
Positives and negatives. Do I have them right? I just wrote positive without thinking. Are they all positive? Remember, we're reading this from here. Is that X positive? Yes. Is that Y positive? Yes. Is that Z positive? No. There, fixed. Do you see why they picked 700 for a force? Wasn't that nice of them? 700 divides by 7, and it's 100. So force C is 300. Force Y is 200. And force K is 600. Do you agree I can write it like that too? Now it'd be dumb to write one of them with vectors and the other one with I's and J's and K's. But again, the only reason that's there is just to make sure 160 gets added to the right number down here. Doesn't really matter how you write it. So kind of dumb for me to write it this way. And again, if I did do this, I probably should put parentheses around this and say newtons at the end, just so that I realize those are newtons. The I, J, and K are just placeholders for which one's X, which one's Y, which one's Z. So I can now move on to, I'm going to change colors to force resultant, which I get by adding them. And I can pretty much do that in my head. 160 and 300, 460. So force resultant is, I'm kind of lazy. So to me, the vector notation is faster. I don't want to write plus signs. I don't want to write I's, J's, and K's, but they all have their advantages. Negative 240 for B and positive 200 for J in the C one is actually a net of negative 40. So that means it's actually, since they're both working together, it's actually resulting in a negative pull, but it was kind of a tough fight there. Do you see? One big negative, one slightly smaller positive. And then what happens in Z? Well, they're both pulling negative. So we're going to get a gigantic negative number here, 1,080. Again, if the question asked, what's the resultant force? I'm done. I just gave it to you in vector form. Did they go on and ask me to, list the magnitude and the direction and so forth? If they did, then I'm gonna have to keep going. But I'm done right now. That's the result. What the problem is. Dang it, same thing. Determine magnitude and coordinate direction angles of it. I don't get to stop. Fine. Learn the language. Magnitude, don't write the word magnitude down. We have a symbol for that. You should get 1174.6. What are you going to see in the back of the book for this? This is a tricky question.
How many significant figures do we have?
It's always 3. You write 3 numbers as an engineer every time. You can't write 117 or it looks like 117. So 1175, that's not what you're going to see in the back because that's 4 numbers. Too many. People get confused when there's too many numbers.
1,170.
It does not mean rounding it down. That's an excellent guess. In other words, put a 0 in there because that's taken away 5 newtons and you don't want to lose that. Well,
So then do you always round up just to save space for extra force?
What you would see in the back is 1, 2, 3 decimal places, 1.17 kilonewtons. That's what you'd see in the back. Do I care on a test? Do I care on your assignment? No. Now, having said that, do you agree that we just wrote what Aaliyah said? Does it make sense? We just lost, that is 1,170 newtons. You see what I'm saying? Like we just lost the rest of it. But again, what engineers say is, that's not very many newtons. Like we're not going to design it so close the bridge falls down, and it's worse to like transpose your numbers and get it wrong. And so we're not writing more than 3 numbers. That's what engineers say, and they're right. That's a great idea. So that's what you'd see in the back. Does it mean you're wrong if you wrote 1174.6 newtons on a test? No, I don't even care. So when you look at the back of the book, go, oh yeah, that's right, I forgot. I mean, that's what you should think. But you need to understand this. This is the language they speak in. Beautiful. We're almost done. I'm a little over time, but we're almost done. Again, the rest of this is really easy. Because to get, and I'm going to write this different this time, cosine of alpha is equal to, which is the x one, is equal to the x resultant, which is 460, divided by this last answer. Now, again, I want to be a little careful here. I'm going to write 1174.6 because I want to get the answer right to the 10th place. And so I can't stick 1.17 in there. I can't stick 1170 in there. I want to leave it accurate because I'm still working with the calculation. So now if I say inverse cosine of that, then I get my answer, which is 66.9 degrees. Again, 3 significant digits. Cosine of beta, I'm going to try to write my beta a little bit better. -40. Oh, notice that's a really tiny number. I wonder what's going to happen as a result of having a really tiny number on the top. Really tiny number on the top. 92-degree angle. By the way, where's the rest of the significant digits? Where's the other digits? It must be 92.0. Does that make sense? You get 92.0. So you can write 0.0. That's actually a good thing to do because it tells someone you have rounded it accurate to the 10th place, whereas this makes it look like you rounded to the nearest whole number. And so that is actually good form to say that to yourself and other people. But again, I don't really care. I don't know about you, but I'm thinking, what? Why is that so big? Well, we don't have time, but draw the picture and maybe you'll see. Like 40 divided, isn't that like pretty much 0, the inverse cosine of 0? Lastly, what's the cosine of gamma? Well, the y coordinate was -1080 divided by our same number. So gamma works out to be 157 degrees. So there's all of our coordinate direction angles from the X, Y, and Z axis. There's our actual resultant force. And so now we know what's happening to the flagpole, and then we can go figure out how many bolts to put on the ground and so forth. Resolution of many forces into one force so that we can figure out how to build a bridge. That's what chapter 2 is. And I think I've given you enough examples here that you can get all the chapter 2 questions correct. But these are tricky. And so as I said before, all the right answers are in the back. If you do your work, don't erase it if you get it wrong. If you do your work and you don't get the answer in the back, then you and I have a conversation about it. You should get 100 on all your homework assignments. If you run out of time or you're lazy or whatever and you don't get them all done, you won't get all the points. If you turn it in and it's wrong, you won't get all the points. I am going to look at the work. You can't just write the right answer in the back of the book at the end of a bunch of work that makes no sense. And obviously, the more important thing is you're going to fail this class. Like you got to be able to do it on a test where you don't know the right answer. But bug me until you do get the right answer. Does that make sense? So this is ultimately not hard, but listening to me say it once is not enough for you to agree with me on that. So there's, I mean, I wish we had time. I could do 6 more examples and we'd all get a lot better at this. I wish we had time to do that. I'm going to have prepared more examples than I was able to do. But Tuesday, when I see you again, we'll be starting chapter 4. You may notice it went out of order. We skipped chapter 3. I have good reasons for that. So I want all of your chapter 2 homework emailed as PDF docs to me over the weekend, or at least by Monday. And then I'll grade them and put them in the grade book so you can kind of see your progress in My Open Math. I'll use the My Open Math grade book for all of that. And if you want to talk this weekend, send me a text, and if I can pull it off, I'll get together. I am going to be sitting in my my office hour Zoom meeting for the next hour. So if you want to, and by the way, if you want to just sit in there and work on your homework, and I'm working on my work, not talking, you're working on your work, not talking, and the whole hour goes by and you had no questions and you're like, bye. Is that hurting any of us? But I'm just sitting there. So if you want to ask me questions, then you can. Totally fine with that. That's not wasting my time. You don't have to have your questions all stored up. We're about where I'm telling you we're going to be every day, 12:30. I mean, I'm supposed to let you out at 12:20, but I probably never will. It just seems like it always takes more time. You okay? How you doing? Does this make sense? You tracking? Anything you want to ask in the closing minutes?
You said by Monday. Do you mean by the end of Monday,
Yeah.
or by the before Monday starts, like Sunday?
I'm always thinking in preparation for the class. And I'm saying that for your sake, because when I start talking Tuesday, I'm going to think you now understand this. So in a sense, I really mean, if you're going to really push it to the wire, I mean by 11 o'clock on Tuesday morning. That if you get it to me before the class starts, I'm just going to look at my email and see what the time is. And I am putting the pressure on you there, because I'm taking points off if you don't do that, because you got no chance at understanding this class. I mean, it builds on itself. You're going to need to understand this deeply so that chapter 4 is easy to you. We got new things to learn in chapter 4. We can't be learning chapter 2 and chapter 4 at the same time. So just get it to me before then. So I'm assuming if you turn it into me, they're all right and you feel good about it and we don't even talk about it. What else?
I was having a hard time getting into the My Open Math, but I don't know if you want to go to your office hours Zoom location.
No, let's just stay here right now. You tried, and what do you think didn't work?
It said that the instruction code was wrong, or the like the class code was invalid, I think.
Yeah, which may be my fault. If you use the one that I think I ended up with an obsolete one sitting in Blackboard. So it's the one I emailed you home is correct, but let me pull it up right now. I'm going to share my screen. Do it right now because this will take 1 second if you have it right. So basically the problem you're having is my fault is what I'm saying. Could be my fault. And I sort of wish I hadn't put capitals into this, but it turns out the capitals and the spaces matter. So course ID 62450 Gardner Winter 2021 with 1 space between those. If you don't type that, it's not going to work. Try that.
It worked this time. I think the enrollment key is different on the original syllabus, but
I didn't realize I changed the syllabus and didn't realize I'd already posted in 2 different places. So I know I sent you the right one, but the Blackboard one was wrong, which is totally my fault. So.
I have a quick question.
Go ahead.
Yeah, from the homework, the question 47, and there's like a few more questions have the same problem. There is the angles. Can I share the screen?
Yes. Let me give you the power to do so. Let me remember how to do that. Seemed like there was an easy way to do this, but I'm just going to make you a co-host because that's the easiest.
Okay, can you see it?
Yep.
Okay, so here we got the angle 30 and the angle 20 right here.
Yep.
Right? But when we're gonna calculate our what we was doing, the resultant, when I put an angle 20, it actually wanted angle 70, not 20. I just not really understanding why they want angle 70, not 20.
Well, it just depends what trig equation you use. In other words, because the theta is 20, then the angle between force B and Y would be 70. And so if you choose to draw your right triangle against the Y-axis, you'd be using 70.
Mm-hmm.
If you chose to draw your right triangle against the X-axis, then you'd be using 20. So against the X-axis, you might be using cosine. Against the Y-axis, you might be using sine.
Mm-hmm.
So they both work. 20, I'd be using 20. I just draw pictures of stuff. I think that makes more sense.
Okay.
Are you, did you pay for Chegg? Is that what you're looking at when you say they used? How did what?
About what?
Did you pay for Chegg so that you have something to look at for help, or What do you mean they use 70? How do you, I just want to know what
No,
people.
no, I was just like
I don't care.
calculating using different angles, and now I got it.
Yeah.
They just gave us a 20, angle 20, and I tried to use angle 20, but it didn't work because I
Yeah.
probably just set it up the equation wrong.
Well, you know, did you notice a minute ago we just used cosine every single time, we never use sine? If you are against the axis, then you can use cosine every single time.
Mhm.
If you're not against the axis, then you got to think a little more because maybe it's sine. With 2D, I tend to draw the right triangles because I can see it and I want to think. I don't want to just mindlessly use formulas. But that's kind of the reason for that. So you can use cosine every time if you,
Mhm.
you just stay against the axis it's referring to, and that's why they use 70, because it's 70 from the y-axis, and then you can use cosine. But if you go from the other axis, then maybe it's sine. Does that make sense?
All right. Thank you, Doug.
Yes.
All right. See ya.
Later, my friend.